So, let's get started. I could spend a whole bunch of time, like 3 days on this section, going in depth on the calculator stuff, and getting you to enter all your data and showing the equations, and same thing we did with the first example yesterday. But I'm not going to do that. I'm not going to go super in depth. I'm just going to hit the overall trend of things and show you how that looks. So, exponential model. We did this at the end of class. Log of both sides. They add out. Exponent goes out in front. So, exponential. So in other words, like a 3 to the x, 4 to the x, e to the x, any kind of exponential model. When you graph it, you should be graphing the log of y versus x. Now, as it says at the top, if the model is logarithmic, then you want to be graphing x versus y versus log of x. Y versus log of x. And hopefully that should make sense, because that's what a logarithmic function is. It's y equals the natural log of x, or y equals the log base whatever of x. So.
Entire unit based on the idea that we know logarithms. Okay. What are logarithms? Okay. What is log? Yeah. Is it like a certain constant number that log is?
No. I can back up and talk about that. I just want to make the distinction, and then I can back up and talk about like logarithms in general and what they are.
That was like the 1 week that I was like gone in pre-calc earlier. No, even if you were there. Okay. I was gone the other day. I just don't mentally. I don't mentally.
Let me keep going through, and then we'll come back when we're talking in a broad scope about them. I want to make sure I get through everything today. All right. So remember, log of A and log of B are just numbers. They're constants. Log of Y is still a variable, and you would usually, when you write the equation, have a y hat. So when we transform, this is another slide that talks about how the logarithms work. So feel free to read that slide. But here's an exponential model. And again, I am not going to be giving, I'm not going to have you enter all this data in your calculator, especially since the numbers get in the millions and billions, and do all that. But I just want you to watch that and pay attention to the fact that when I graph, since this is an exponential model, if instead of y, I start to graph log of y, then we get a linear model. No, this is exponential.
I don't either, but I thought exponential is only the curvy one. Exponential can't be the curvy one.
No, exponential is on this trend.
So what is exponential into linear?
So exponential means the model is in the exponent. Exponential means the model is the variable, the x, is in the exponent. Versus the ones we were talking about yesterday, which were polynomial functions, like x squared and x cubed, they called the power models, because it was x raised to a power. Now the exponent is in the variable, so we call those exponential models, exponential functions. Okay, and then we have logarithmic functions where x is inside a log. So for exponential, like this one, which shows an exponential growth, you would put x still on the x-axis and log of y on the y-axis. And so when that happens, it will make it a straight line. So the main thing that you will need to notice for that, so we have a linear pattern between x and, in this case, they use natural log. We can use any base log, but they use natural log. And the main thing that you will need to know how to do is to take this output, the computer output, and make sure you know how to get the equation from there. So let me talk through that. It is the same thing. It is the same structure as your usual equations for lines. Except instead of y, since it's exponential, instead of y hat, we're going to put log of y hat. But then the right side of the equation is still going to be the same. The constant is my y-intercept, and years since 1970, that's my x variable, and so the coefficient of that is my slope. So the way that this equation is going to get written is, since I use natural log, we're going to put natural log of basically y hat. They just say what y is, the transistors, equals, here's the y-intercept, plus, here's the slope, times x, which is years since 1970. So the difference is that instead of y hat, we're using log of y hat, or in this case, they're using natural log.
Why are you pulling in from the first one instead of the second one?
Say that one more time. Pulling what?
The numbers that we're getting in this, wait a dang minute.
So these numbers are the coefficients. Are you talking about the first column? So this number is from the first column. This is the constant y-intercept.
I thought that it follows a row.
The SC coefficient is in an equation. That's not the constant. That's not the y-intercept.
This is standard error that we used for the confidence intervals and stuff from the last chapter. Here are the coefficients we use in the equation for the y equals mx plus b. Since this number is attached to my variable, that's going to be my slope. And so this is slope. This number is a constant, so it's the y-intercept. Right? That's been the case all the way back since chapter 3. But now the only difference in the way we write the equations now is that instead of, for exponential, instead of y, we're going to put log of y. So let me show that very quickly. So in this case, natural log, and we put a hat above it, define the variables. Here's slope, here's y-intercept. So we can keep, so we can use that model to make predictions. So for example, this is another thing that you'll need to do. Is that if the number of transistors in the chip in 2020, and so years since 1970, how many years is 2020 from 1970? 50. So we put 50 in for x, and we get 25 out. Okay, now here's where logs come in. So this is natural log of y hat, or the hat goes above the whole thing, equals 25.3562. And so remember, the answer to a logarithm is an exponent. So this number is telling me that this is the exponent I want to use when the base is e, in this case, since we're having a natural log. Natural log uses the base of e. So I can rewrite this to say that e to this exponent equals y hat. So that's what you're going to see them do here.
So then what happens when we don't use natural log?
Which is
E get replaced with?
big number times, this is times 10 to the 11th. So if we're just using log of y, the log is base 10. So if there's not a number down here, assume base 10. If it's natural log, the base is e. If it's any other base, then we have to say that. So if I want the base to be 8 and talk about 8 to a power, then I need to say log base 8 of, say, 64, which is 2. Because the exponent that I need to put above 8 to get an answer of 64 is 2. Residual plot, record your observations. There's our observations from the residual plot. Again, I'm going pretty broad strokes here today to make sure I get through everything. All right. So we have one more example here, and it's with another power model. Now, in the other ones, I told you, oh, it was squared. It was cubed. It was, that was the model. But if we want to just fix it to some kind of exponential growth, then we are going to, we can use logarithms so that we don't have to know exactly what exponent we are using. So let me show you the way that that's going to look. So if I have ax to the p, so p is the power, the exponent, and these are numbers, and x is my variable. So I'm going to do the same process I'll show it out here first. Y equals ax to the p. So I'm going to take the log of both sides. Log of y equals log of ax to the p. And we're going to use the same two properties that we used the last time we did this. It's the same exact steps. It's just that things are rearranged this time. So we are using the fact that since it's multiplication, I can extend it out, write it out with addition. So log of a plus log of x to the p. And then, again, same thing we did last time I showed this. Since there's an exponent up here, another property of logs is that I can bring that exponent out in front. So I wind up with log of y equals log of a plus p times log of x. So two different things to notice here. First off, instead of this one's log of y versus x, this is y versus log of x, power models are log of y versus log of x. Those are the three different models that we can use. The other thing to notice in the power model is that, let's say I didn't know what the exponent was. Like I didn't know whether it was an x squared or x cubed or x to the whatever power model. And I want to figure out what it is. Well, let's take a look at where my exponent ended up when I went through the simplifying. Here's where it was, the p. Where did that end up? It ended up right out in front of my log of x. So what power are we raising it to becomes the slope when I write it in my mx plus b format. So let me show the rest of the slide just so that you see that. And then question.
Oh, so earlier you said with exponential, the variable is in the exponent. With logarithmic, the variable is with the log. And then how about power? Where does the variable end
The
up?
variable is the base. So you'll notice that it's x to the p. So x is the base, my variable is the base, and then it's raised to some number.
So it would be like x log thing.
No logs in this format. It is like x cubed is a power model. X to the fourth is a power model. 4 to the x is an exponential.
Okay.
The main ones to know the difference is between exponential and power. Powers, we're taking x, raising it to a power. Exponential is we are putting the variable up in the exponent. So showing that simplifying again, the power becomes the slope of the line. So again, if we scale instead of graphing x and y, we graph log of x and log of y, we should get a straight line. So let's watch that happen with an example. So we know this is some type of power model. We don't know which. Strong positive curve relationship between the distance from the sun and period of revolution. And we are very, and astronomy is very egotistical by using the, AU, distance from the sun, is distance from the Earth is 1 because we're the most important. And then the period of revolution, we're using the amount of time in Earth years because we're the most important. So again, let's watch the exponential model happen. So if instead of graphing x versus y, here are the scatter plots. So I have two different ones here. I have the one on the left here, which is graphing AU on the x-axis and natural log of the period on the y-axis. And then this one graphs natural log versus natural log. So which one is which type of model? This is graphing x versus natural log of y. So this would be testing what kind of model on the left? Exponential. And do we think that exponential is the best model? No, because not a straight line. This is graphing natural log of x versus natural log of y, which is power. And so that's why our power model is better than an exponential model. Because the scatter plot of natural log of the period versus distance is slightly curved. So exponential model bad. Natural log of period versus natural log of distance, power good.
That's how you need to explain the rest of this unit to me. I mean it. Also, question. Earlier we said, so like when we did the 3 steps, you know, the strong, positive, and then we talked about like linear, in the earlier units.
We would say linear.
Right.
And this one on the last slide, we had said that it was a curved pattern.
So could you have said exponential instead?
And, well, now we want to say power, because power good.
Right. But
So we would want to elaborate and say a power model. So right now we would want to say curved. We would start by wanting to say curved, and then a hypothetical part B of this question might ask, okay, it's a curved model, which one of these 3 should we be using
to make it a linear model.
to make it a linear model? So we are choosing the power model to make it linear. Okay, that's the broad idea. Now to have a little bit more detail, to come up with the least squares regression line here, again, we're using natural log, so log with a base of e. Natural log of the period equals, and then again, we're using y-intercept here, we're using x here. We're making sure we put a hat above the y piece of that coordinate. And remember that our slope of the line tells us what power to use. So this tells me, the 1.499 tells me that this is basically like an x to the 3/2 type of model. That the relationship is about an x to the 3/2. If I were to rewrite it as a power model. Okay. Here's your model for part B to predict the revolution period for Eris, which is 102.15 AU from the sun. Show your work. So that means our distance is 102.15. So we are going to plug in here. So to fill in a step, they are doing 0.000254 plus 1 point plus, oh man. Let me start that over. Times the natural log 102.15. And so natural log of 102.15 comes out to be about here. And so that's how we would get this number. We would basically put this thing into our calculator, get out 6.939, and then say, since natural log of y equals 6.939, natural log is a base of e, so that tells me that e to the 6.939 equals y hat. So our prediction should come out to be e to the 6.939 which is about 1,032 years.
Will our calculator immediately know what to exchange E for?
There's an E button in the calculator.
Gotcha.
All right. So since the natural log of distance is about 6 or close to 7, oh, sorry. Natural log of 102.15 is, this is what we need for part B, 4.626. Okay? So that's about over here. So this is a residual plot question. Okay? What I'm about to ask is a residual plot question. Here's the x value for natural log of distance, is the 4.626. Should the residual over here be a positive, be predicted to be a, would you expect it to be a positive or a negative residual? Think about where the rest of the points around there grouped. In this region, it's about a negative residual. In this region, it's a positive residual. Right? So we would expect this residual to be positive. So if the residual is positive, which one is bigger, the observed or the predicted? Observed, because residual is observed minus predicted. So we'd expect the observed to be above the predicted. So in other words, here's my prediction. We would expect that prediction to be a little bit lower than my observed. Now will it go on? No, it won't. Okay. There it is. At the far right, where all the residuals are positive, because residual is actual minus predicted or observed minus predicted, seems likely to be positive, we would expect the prediction to be lower than the observed. So, key things to know. We are still using the same way to write equations of lines that we have been. The only big thing that needs to change is that when we are plugging things in, we might need to use some logs and e to powers and 10 to powers to account for our use of logarithms. You should know which one of these three to use and be able to tell them apart based on which one of these we're writing or putting on graphs or they're showing the computer output for. You should be able to match it and say, oh, that's power. So those are the main ideas. And then same ideas that you should know for like scatter plots, interpreting slope, interpreting y-intercept, knowing what r squared means, knowing what a residual is and residual plots are, all that good stuff. But mostly the new stuff is going to be focused on having, knowing which between exponential, logarithmic, and power to use.